Welcome to TOC lecture series. Today we are going to see that not every language is a regular language, and it is bit quite natural that we already know that natural languages are of finite memory, and in the DFA or NFA setting, it cannot remember the previously read symbols or the number of previously read symbol to match the next coming signals. For that, for example, in this case, this language L1, there are N, A, and B. So it is not possible for regular languages to recognize such strings. So how to prove that certain language is not regular? It is used using a very popular lemma called pumping lemma. Pumping lemma basically based on pigeonhole principle. It verifies that after taking n symbols of it, it is not repeated again. Okay. So let's see what is the statement of the theorem. Suppose L is an infinite regular language, that is there are infinite number of strings. Then there exists some positive integer m such that any string w which belongs to L and the length of the w is greater or equal to m is an integer m. In that case, we can decompose the string w into three substrings x, y, and z, where this would be xz. Length of the xz should be less than or equals to m, and length of the y should be greater than 1. That is, there should be at least one y. So such that we get wy and any number of y. So we are this is the state which we call it pumping. So you can pump y any number of time. If after pumping any number of y in the string, if still it belongs to L, so we can say that but that language is regular. If any time happens that this does not belongs to y L, so in that case we can say that this is not belongs to L. So by contradiction we can prove that any language, suppose L1, L2, anything one, is not regular. So how to prove that? So proof of this pumping lemma is very simple. Let's say language L is equal to L A, where A is some DFA. Okay, now let string W A1, A2, AM, where M is greater than N. That is, the length of the string is greater than the number of states of the DFA A. Now let's find states pi, that is after reading I symbols. So we can get using our extended transition function. We start with Q0, that is the initial state. then reading I symbol, we reach to Pi. Okay, in a particular case, the trivial case, P naught equals to Q naught, and we have to find for each I, that is I equal to 0, 1, okay. So we can say at this point that if the number of inputs is n plus 1, so we can say that uh, there cannot exist n plus 1 distinct states, because our system A have a number of states. So let's again assume two integers I and j such that and I cannot be equal to j. And say Pi equal to Pj. This will happen when there is a repetition. Okay. So now we can have a string W decomposed in three substring x, y, z such that x equals to a1, a2, ai, y equals to ai plus 1, ai plus 2, aj, and z equal to aj plus 1, aj plus 2. So we have three decomposed substring of W. Now this particular situation can be visualized by a DFA diagram as that is, we read x here, so go to Pi. In this particular case we are reading y equal to ai plus 1 to aj, then we recognized the last portion, that is j is equal to aj plus 1 to an, and reach to the final step. Okay, so now we have to see that W x y k z belongs to L or not. So start with k equal to 0. In that case, W becomes x and z. So we can say that after reading I symbol, that is x, is to p, and since there is a no y, so it goes to the final state. So xj, sorry, this should be xj belongs to L. For k equal to 0, k greater than 0, we get that for reading x part it goes p0 to pi. For reading y it goes pi to pj, where pi equals to pj, and then for reading z it goes pj to the final state. So in that case also we can say that W belongs to L. So the particular language L, since it is proof for any arbitrary string, so we can say that W, the L, is regular. To disprove that L is not regular, we have to show any counter example, and it is if it is does not belongs to L, any string W, then we can definitely say that that particular language is not regular. So let's take an example. Suppose L 0. Now uh, suppose pumping length of W is M, so W now becomes p to the power M. Now assume there is a decomposition of W as such yi b, where x equals to m minus k, y equals to k, and z equals to for I equal to 0. What is the form of the W? A. Now according to language, number of A and number of B should be same for any string of that language. Now, but in this case m minus k is less than m, so this string, the W for I equal to 0, does not belongs to L. So we need not to go further because one counter action is enough. But even we want, then we can go for I equals to 2 again. Then now k for y ak 2 pm. Now in this case number of a becomes m plus k, and this is m. So again we can say that this particular string does not belong to L. So A to the power b to the power, this language, particular language, is not a regular language. We can also, in the second example, let's example 2, where the language L is like WWR, does that W belongs to sigma star, and suppose 0 1 belongs to sigma. So in that case, we can rewrite this language as, so there are the strings of zeros and 1, and for the string 0 and the reverse of the string 0, there will be uh, two copies of zeros and ones. So we can write this as 0 2 to the power n 2 raised to power. Okay, 0. Now let's assume a string any w of length m is decomposed as yi z, where x equal to 0, y equals, and z equals. So from this language we know that there should be even number of zeros and even numbers of ones. Now choice of k actually determines whether the language whether any string of this kind belongs to this language or not. So if we choose k even, what happens? For I equal to 0, w, we see the w as 0, k, and 1 to the power p. So in that case we see that this is even, this is also even, because k is even, so this belongs to L. And this is not only true for I equal to 0. If we take any value of I greater than 0, this also leads to the same calculation. Now the second case, this is the first case. In the second case, we assume that k is odd. Now we'll see that I equal to 0, w, now there is a possibility that this 0 is odd, so this does not belongs to language L. Now if you take higher version of I, higher value for I, suppose greater than 0, I equals to 2, suppose. So w belongs to k 0, k, to p. Now what will happen in this case, that twice of this odd, this value, this becomes even, but this portion is odd. So odd plus even, suppose we take an example. An example. Uh, 2 plus 3, 5, 7 plus, sorry, 8 plus 3, 11. So you can see even plus odd gives an odd value. So even if this again, if we minus 3, 3 again odd, so this odd, this even, so total becomes odd, and this is even, so this does not belongs to L. So you see that this language does not belong to, sorry, any string does not belong to regular language, and a particular choice. Also, in this example, we prove that we need to show any counter example to disprove the fact or prove the fact. So, for problem like this, that we want to show that particular language does not belongs to a regular language. So it is very pretty simple that we have to get one value of I for which this string does not belongs to L. In case of any language belongs to L, we don't need, we always know that any value of I, that string, any string, will belong to the language. So in this way, any problem of like this can be solved by approaching very pretty straightforward way. Thank you.